Hey guys, welcome to my algorithms video on the cost distance metric. My name is Dalton, and I thought I'd introduce myself real quick since most of you have never met me. I came to Bozeman this summer, starting a master's program in computer science, and my undergraduate degree is in environmental science, and I say that because this presentation will be at the intersection of those two things. So without further ado, let's get to it. So I did forget to introduce somebody earlier. This is Verna. She's been my classmate in this room all semester long, and she's going to help us in a little bit understand what the cost distance metric is. Verna. All right, we have moved inside the computer. Welcome. And like I said, we're doing the cost distance metric. My subtitle for that is Taking the Shortest Path Problem Out of the Maze and Into the Wilderness. I'm hoping that this will be a good bridge between some of what we've already learned in 432 and some new applications and extensions. I do have a lot to cover, so I'm not going to go through this outline list. We will have to go pretty quick to try to keep it all within the time frame. All right, so we'll do a quick review on metrics real quick. Remember that a metric is just a way to measure distance between two things. And those things might be kind of abstract. And then we say the set of all things is the metric space. Metric space must have some certain properties. The identity of indiscernibles says that if the distance between the two things is zero, then they must be the same thing. Symmetry says with a distance from x to y, that has to also be equal to y to x. And then the triangle inequality says that it's shorter to go between 2 points than it is to get between the same 2 points by going through a third. And we've got a bunch of different metrics that we've been exposed to all our lives. Euclidean distance is our intuitive notion of distance, just linear. The geodesic is how you move along a sphere. The taxicab metric I thought was interesting. That's right here. In this example, the yellow, blue, and the red lines are actually all the same distance because it's based off of the absolute difference of the x, y coordinates. Graph metric, we've studied a lot. That'd be like Dijkstra's algorithm for shortest path. And then one interesting example, more abstract, was the Levenshtein distance, which is the distance between the strings. So here we'll be talking about the cost distance metric. So it isn't. All right. So I think I promised you guys cats, and here they are. So this is just some B-roll from my kitchen of my cat's favorite places to hang out in the house. As you can see, they're up on top of the cabinets. And so, what I would argue at this point in the presentation is that there is an optimum path for them to get up there, and that path can be found algorithmically. Now, looking at the kitchen, and you should take just a brief note of its layout because it'll come back up. You could imagine what that path would be. All right, so the next piece to talk about is called the friction of geography. First off, the friction of distance is the idea that moving a distance costs something, whether it's time, energy, money, or some other resource like gasoline. To move through space costs something. The friction of geography says that the space you're moving through may cost more or less than some other space. So consider it this way: there are many ways to get to the top of the mountain. You could climb straight up the cliff face, which would have the shortest Euclidean distance, but maybe a really high cost physically for your body. Or you could take the nice, easy hiking trail. It'll take you longer. You'll go farther by Euclidean distance, but at the end of the day, it'll be easier to do it. So now we're at the cost distance metric, which is a way to analyze distances across a continuous surface that is also weighted. And we call that a cost surface. The way I would think of it is, right now at least, like a quilt that's been laid down on the earth, and each patch has a certain value, what it takes to move through it. And your least cost path is the collection of quilt patches that you have to move through that's going to connect you from where you are to where you want to be and minimize that total accumulated cost. Um, First off, this is not a new idea. It was introduced in 1957, but is still very relevant in the literature today, especially in applications of computer science, not as much in theory, but you see it in all sorts of disciplines. I actually ended up on this project because I was interested in studying Dr. Sean Yaw's at MSU's research in carbon capture optimization systems. And upon looking into that, I realized that it's really a whole suite of software, and the cost distance metric or least cost path algorithms were a component of that software. With that said, if a solution to a spatial problem is already confined to a pre existing network, say, for example, like Google Maps routing you from your house to a restaurant, there is a road network there, and Google Maps will default to that network. They're not going to do a least cost path and send you through a field. Um, but cost distance metric is especially relevant when that pre existing network does not exist and you have the freedom to move anywhere you want in the world. So, having talked about friction of geography, let's bounce back to the cat problem real quick. What is the optimal path for the cats to go from floor to top of cabinet? And before we get into solving it with a cost surface, I would say, could that problem be solved with a simple graph structure? Probably, but it might get messy. And so here I'm just trying to build an intuition for cost surfaces and kind of advocate for why they should be used in these situations. Again, the cats can go anywhere they want. And so there is no network that they are confined to, and placing nodes might be complicated. So let's start by just kind of laying down a kitchen, the layout of my kitchen, and we'll build from there. The next step's pretty simple. We're just gonna lay that quilt down, a grid, across this model of the kitchen. And I would take note of how some surfaces are half in one cell and half out of the cell, and what that might mean for the friction of geography to transfer between surfaces. Also, take note that I dropped a start point and a destination point, the source being the red circle in the bottom left, and the destination being the gold star in the all right, so we take kind of a big jump at this step because the grid became filled in. And the first thing I want to talk about is the key in which it was filled in. If the cat could move from one cell to another without jumping, then I would give it a value of 1 and color it green. If it had to jump less than 3 feet, I would color it yellow and give it a value of 10. And if it had to jump over 3 feet, then I would color red and give it a value of 1,000. Where did 1, 10, and 1,000 come from? They were totally made up by me, somewhat intentionally. I did want over 3 feet to be this somewhat impossible barrier because my cats, I have never seen jump that high on their own free will. Um, so now we've got a cost surface, a quilt, patchwork of different frictions of geography for the cats to travel through. Now you might be wondering, well, how did he assign those values? That's totally fair. That happened fast. So I've gone out of present mode and we'll just do this manually real quick. I'm gonna turn the grid on and off, and hopefully you can see that it's at the boundaries where they have to jump that they have a very high friction of geography. Um, and the higher the jump, the higher the friction, just like climbing a cliff to get to the top of the mountain. So the question remains, well, what is the least cost path? And I will say, full disclosure, I did not actually run this algorithm on my made up PowerPoint cost service. I did this because I've seen my cats get on top of the cabinet so many times. And here is the least cost path. I am excluding diagonals, which we will talk about later. That is allowed in the world of GIS. Um, But basically what they do is they walk over until they've got a straight shot at the countertop right next to the fridge, and then it's the fridge that lets them get onto the cabinet. And these values here are the accumulated cost as they walk this path. Coincidentally, it turned out to be 50. Didn't plan that. I would say though that note that the 50 is unitless. Um, I made up those numbers 1, 10, and 1,000. There are no units to that. It's not feet, not pounds, not joules. That is a unitless measurement. Whereas the Euclidean distance, and I did actually measure this from the floor in the entry of the kitchen to the top of the cabinet, that diagonal is about 10 feet. Okay, if you're somebody who needs to see it to believe it, here is footage of Verna taking that least cost path we just came up with. Um, Funny story, she wouldn't do it when we tried to force it with her dinner. So we set up the trail cam and caught her later on in the evening, scurrying up there. But I think that is kind of indicative of how um, organisms, wildlife, will travel the easiest way they can. And that's why biologists so often use least cost path algorithms to model the movement of megafauna in the wilderness. All right, maybe seeing the cat example was helpful, maybe not, maybe it was trivial, I don't know. I would be curious to hear. But now we can get into the actual wilderness, modeling large expanses of land where the solution is not so easily recognizable. And to do that, it requires something called GIS, which is Geographic Information Science or Systems. And it's all about organizing, analyzing, and displaying spatial data. When we say spatial data, that means that there is a georeference to a physical location on planet Earth. That's different than data that could be anywhere. This is tied to a certain point on the planet. And it is really at the intersection of cartography, map making, and computer science, personal passion and interest of mine, but it's also found itself in pretty much every discipline you could imagine. There is a spatial problem that can be solved with GIS. And so, a couple heavy hitters in the software world that you hear about is Esri's ArcGIS, and then an open source platform called QGIS. And then these are just two Instagram images I lifted off of Esri's Instagram. That top one of South America is if forests were mountains. So they render it 3D based on the abundance of trees instead of elevation. And then that bottom one is a map of where biodiversity and human density collide. Before we talk about the algorithms, we've of course got to talk about the data structures in GIS. There are really only two, and they're not too complicated to understand. They're called vector and raster. You might have heard of them even in contexts outside of GIS. Simplest put, vector is points, lines, and polygons. They represent features on planet Earth, something you can point to and say, that is a river or that is a fire hydrant. Whereas a raster is a matrix of cells, and that would represent a continuous surface. Um, Given that the cost distance metric is about moving through continuous surfaces, we will be living in raster world for the rest of this video, but I thought it was important to mention both of them. And there is this GIS slogan, raster is faster, but vector is corrector. And I think if you look at that image of vector versus raster, you can see that an algorithm implemented on a raster is really just kind of like iterating through a multi-dimensional array, whereas a vector would have some challenging geometry going on there. Lastly, I'd just add that vectors and rasters do present themselves elsewhere. For example, a raster is a collection of pixels that makes up a picture. So Adobe Photoshop that operates on pictures is a raster-based program, whereas Adobe Illustrator that's used more for like logo design would be a vector-based program. And I'll show you an example of that in a little bit in the GIS world about how they're different. And then the algorithms are just tools that manipulate those data structures. So I think it makes the algorithm seem a little more palatable knowing that it's points, lines, and polygons or it's cells. Okay, so we are going to bounce over to the world of GIS a little bit. This is Esri's ArcMap. Um, in here, I can display data. Hopefully the shape looks familiar. This is Gallatin County, and it is a polygon. It might look like a raster right now, but it is actually a vector or shapefile. And I'll show you the other two examples of shapefiles. Vectors are rivers. Those would be lines. And then the points. Here I've got a source and a destination that will be relevant when we actually implement the least cost path algorithm. But one important thing to note about vectors, and this is same is true in Illustrator, is when you zoom in, they keep getting finer and finer. So you don't have a loss of precision. They are tagged to an exact point. That is not true about rasters. They do have a loss of precision when you zoom in. So let's look at some rasters. Um, I'm going to throw on what is called a digital elevation model, a DEM. It just represents the height of the land above surface level. And this is in meters, so we're going from like 1,200 meters to 3,200 meters. And hopefully there's some identifiable features here. For the sake of this particular demonstration, we are going to try to implement a least cost path that basically goes right up and over Sac Peak. And I'm just curious, where is it going to go? Is it going to go up here through this little notch? Is it going to go down here through the Ross Peak notch? Or will it go right over? And again, that's going to depend on our cost surface. But anyways, that's brief intro. All right, so we're finally at the point where we're going to talk about actually transforming input data into the output least cost path. Here we have just a simple model where we've got circles representing data structures and the yellow rectangles representing algorithms. So what we need to do to find a least cost distance between 2 points is we need to feed a source and a cost surface into a cost distance algorithm, and that will give us a cost distance data structure and then a backlink data structure, which we can feed in with a destination data structure into a cost path to eventually get the least cost path. That's just a broad overview. We'll go through each of those real quick coming up. You can't have a cost distance metric without a cost surface, so the space for the metric to exist in. So you have to build a raster that will represent that friction of geography. Where is it easy to pass through and where is it hard? That is going to be so unique to the problem, it's hard to kind of generalize it. You can't talk about SwiftFox and power lines in the same way. Often, though, they are without physical units, and that's because what we do is we combine multiple data sets that could not add together unit-wise to come up with a classification of where it's easy and where it's hard to move through. And really, that work is done not by computer scientists at all, but by the experts in the field. So if it's modeling SwiftFoxes, you have the biologists and the ecologists out there thinking about the habitats that SwiftFoxes do and do not like. If it's installing power lines, you have the engineers out there thinking about what surfaces are really expensive or difficult to install on and what aren't. And in our demonstration, we're going to just use one input data structure. So we are not doing a multi-criteria. We're just going to work off of slope. Our slope will be our cost surface. It will be reclassified on a 1 to 9 scale, but essentially just think of it as slope. Know that cost surfaces can get pretty complicated though. Like, you can't even read this one up here, but I imagine it's about an animal, because they have different submodels that consider the habitat, the food availability, and the security of the animal, and all of those things come together to build one cost surface. So once we have the cost surface, which again I think is the hard part here, we can actually implement the cost distance. So the cost distance raster is a raster that at each cell will have the lowest accumulated cost from source to that cell. And the algorithm is surprisingly similar to Dijkstra's shortest path algorithm, or maybe unsurprisingly. You're going to declare a queue and you initialize it with the source, and then you kind of do a best first search outward. If you're at the source, you give it a cost of 0, and then you search in your neighboring cells, of which there are 8, and you find the one with the lowest cost, and then you point to it in the backlink raster, which we'll talk about next, and then you're going to accumulate the cost. So when you find that lowest cost, you're going to add whatever your current cost is to it. And then if any neighbors have a greater value, you add them back to the queue so that they can be evaluated later. One thing to note is that if you do traverse a diagonal for a straight line, you have to account for that, and that's just a simple kind of following of Pythagorean's theorem. You would multiply the cost of that diagonal cell by root 2. This is kind of a bulky method for going about this, and there have been more efficient algorithms to not send so many duplicate cells back into the queue, but for time's sake, can't get into them now. I forgot to mention this here is the cost distance raster, scaled from this light blue into green into red into white, color ramp, um, for this red source on Gallatin County that I ran earlier today. And one interesting thing to note, again, our cost surface is solely based off of slope, and so that has a lot to do with it. But this is kind of indicating that it's easier to travel to Four Corners than it would be to walk over the Bridger Range, which I guess is arguable, depends on how you feel about slope. So we've talked about this thing called the backlink raster, but haven't really explained what it is. It is a crucial part to getting to the least cost path. The cost distance raster that we just talked about in the previous slide is accumulating cost at each cell as it does this best first search outwards. But at any given cell, that cell does not know how it got there. And so we have no sense of directionality, only of magnitude. And so the backlink raster is taking care of that direction for us, by marking 1 of 8 values, and the value marked in a cell is just pointing to the lowest cost neighboring cell. And so you can see it kind of represented up here, kind of starting with yellow and then working clockwise around. Those colors don't actually mean that, but I did scale our backlink raster to those colors, and you can see that it's kind of meaningless, but very important for the computer. Meaningless for the human eye, important for the computer as it goes through cell by cell and traces back from destination to source. Okay, so we're finally at that least cost path, the final thing that we wanted to get to, this new distance metric. What outputs from the algorithm is actually just a collection of pixels. It's still a raster, that goes from source to destination and minimizes the accumulated cost between the two. But how we get there is backwards from what you might think. We've built out our cost distance raster, and that holds the information for really every single cell in the processing extent of whatever space you're looking at. And any destination you drop on it at that point is going to be able to recognize itself, and then trace back to the source. And so building the least cost path from the cost distance raster is just a matter of using the backlink to go from distance to source. Hence why it's called backlink. Uh, and then we end up with our cost distance path. So whether you're a hiker or a grizzly bear or a power company trying to install um, power lines, apparently, according to the algorithm and trusting our input data, this is the easiest way to cross the bridgers from that point to that point if all you care about is slope and you trust how I rescaled it. I'm back here in GIS land, back on the bridgers. I moved our source and destination a little bit just for a quick demonstration, experiment of what would happen. But I really appreciate you going on this journey with me. It's been a blast for me. Now we've got our source up here at this noticeable pass. I don't know what it's called, and then our destination at this noticeable pass, Ross Peak. I'm wondering, is there any way we would just trace around the mountains and try to take a pass as opposed to doing more of a Euclidean move and going straight over? We'll see. I'll run this as quick as I can, and if it's too slow, I'll speed it up when I edit. But the first thing we're going to do is calculate that cost distance raster from the source. And I'm still just using slope as my cost surface. Also working on pretty small extent with this range. So I'll run pretty quick. And then we've got cost distance, which means that I messed it up. I didn't make that link. You have that link, or else it doesn't work. Right. Okay, now I love those, and I can do my path. And so I'm going to put in the destination, and put in the cost distance, and put in my backlink, and see what I get for a least cost path this time. Oh, this distance. A little weird coloring. But you can see that it did that time avoid the peaks altogether. Took the pass. Why wouldn't you? Makes sense. Um, if all you care about when moving through terrain is slope. Anyways, thank you so much. I have appreciated this time we've spent together. And yeah, we will.